Okay, it's 4 parts, so let me get started. My name is Standard Živný. I have the pleasure to introduce the next speaker, Alexandros Hollender, or Alex as we call him. Alex is based at the University of Oxford. He was a student at various institutions in various countries, Germany, France, and the US. And about 4 years ago, he came to Oxford to do his PhD here. And a few months ago, he finished, and we are delighted that he decided to stay on. And he's now, although the affiliation doesn't say it on the slide, he's now the first ever computer scientist at Oxford's All Souls College, where he just started a 5-year postdoctoral fellowship. So Alex, over to you. Looking forward to this talk. And to the audience, if you have any questions, urgent questions, please raise your hand, and I'll give you the floor. But try to keep most of them to the end of the talk, please.
Thank you, Standa. Thank you for the introduction. And thanks to all the organizers for the invitation. So my talk is going to be about the complexity of a problem related to gradient descent and some implications of that on some mysterious complexity classes. This is a joint work with John Fernley and Rahul Savani from the University of Liverpool and Paul Goldberg from the University of Oxford. So let's start by just considering a standard optimization problem, which is you want to minimize a function f over some compact domain, like the unit hypercube. And let's say the function has some nice properties. It's smooth, so continuously differentiable. How hard is this problem? Well, it's actually known to be quite hard. It's known to be NP hard. And in fact, this NP hardness holds even if your function is pretty simple, even if it's a quadratic polynomial that I give to you explicitly, this problem is still going to be NP hard. Now, of course, if the function f has some extra properties like convexity, the problem can be solved efficiently. But for general smooth functions, we know that the problem is NP hard. However, in practice, in machine learning, people do want to solve this problem, and they do manage to do a pretty good job at it. And what is one general approach that is quite successful is to use the gradient descent algorithm. So what does the gradient descent algorithm do? At least, its simplest version. It's an iterative process where you have a point and you compute the next point. And the next point is just computed by essentially updating according to this update rule, which intuitively just says we're going to try to move in the direction of steepest descent. So what we're saying is you look at just the local information that you have at the current point, namely the gradient, and based on that local information, you're going to do the optimal thing, which is to move downhill with respect to that gradient. And there's also a step size eta that determines how far you're going to move. So let's take a look at a picture. Imagine that this is your function, and let's say you start gradient descent at the red point. At every step, you're going to move downhill. So the first step could do this, for example. The next step could take you over there, etc. And you would hope that you end up at a minimum of the function that way. Now, from a theoretical perspective, the gradient descent algorithm is actually not guaranteed to solve this optimization problem. And the reason for that is quite easy to see, is that if the gradient is 0 at some point, then gradient descent is not going to move, it's just going to stay there. And what that means, in other words, is that gradient descent is actually only guaranteed to output a stationary point of the function f, namely a point where the gradient is 0. Now, because we're working in constraint optimization here, and we have a domain, to be more specific, I should say that it's guaranteed to output a so-called Karush-Kuhn-Tucker point, KKT point, which is just a generalization of a stationary point for the setting where you have a constrained domain. But for the purpose of this talk, you can just think of them as stationary points. So how good or bad are stationary points? Well, the problem with stationary points is that the red point over here, which is a local maximum, is also a stationary point. It's a point where the gradient is 0. And so what that means is that gradient descent is not really guaranteed to output a global minimum, not even a local minimum, could even output a local maximum, actually. The question we ask is, okay, so gradient descent solves a different problem. It doesn't solve the NP hard optimization problem. It solves a problem that's perhaps easier. What is the complexity of that problem? What is the complexity of the problem that is actually solved by gradient descent? And you can reformulate this question in different ways. What is the complexity of finding a gradient descent solution? What is the complexity of finding a point where gradient descent terminates? What is the complexity of finding a stationary point? All of these things essentially are the same question. Okay, so once you decide this is the question you want to study, you have to formalize this as a computational problem. And the way we do this is we say, okay, there's the input, you're given a continuously differentiable function f, you're given a step size eta and a precision epsilon. And the goal is to find a point where gradient descent terminates. Now, of course, we have to make this precise. What do we mean by a point where gradient descent terminates? And there's at least two very natural ways to define that. The first one is to say a point where gradient descent terminates is a point x, where the next iterate, x prime, essentially does not improve the function value. The improvement in the function value, the decrease in the function value, is at most epsilon, where epsilon is a small precision that we're given in the input. And if you pick this kind of solution concept, then we call the corresponding problem GD local search. So this is one way of looking at when gradient descent should terminate. Another way is to say, no, actually, gradient descent should terminate when the next iterate x prime is very close in some norm to the current iterate x. So the distance between x prime and x is less than epsilon. Both of these are very natural. And the nice thing is that it doesn't matter which one you prefer, because the two computational problems are actually equivalent, polynomial time equivalent. And they're also equivalent to the question of just finding a point where the gradient has norm less than equal epsilon. In other words, the definition of this problem is quite robust to how you actually define the solution concept. Now, one important point in order to make this definition completely formal is to say how exactly the input is represented. So for the step size eta and the precision epsilon, that's pretty easy. You just assume that they're given to you in a standard binary representation. But for the function, you have a choice to make here. And in optimization, people often study these kinds of problems in a setting where you have query access to the function f and its gradient, let's say. So in kind of a black box setting where you just count the number of queries. But we are interested in studying this problem in the so-called white box model, where you're actually given an explicit representation of the function f. And so the model that we're going to pick is that the function f and its gradient are given as arithmetic circuits to us. So we're given an explicit representation that tells us how these functions are computed, how to compute these functions. I would say that in many applications in machine learning, this would be the more relevant model, because you know how to compute the function. So the definition is now pretty much complete, the formal definition. What is the complexity of this problem? So there is one pretty simple algorithm to solve this problem, which is to just run gradient descent. Okay, that's something that you can do. If you run gradient descent, it's going to terminate at a point where gradient descent terminates. So that's definitely one possible algorithm to solve this problem. How good is the algorithm? So it's known that gradient descent essentially has a running time that's polynomial in 1 over epsilon, which for various applications might be good enough. But in the way I have to find the problem here with epsilon given in the input in binary representation, this actually does not correspond to a polynomial time algorithm, because the algorithm would have to be polynomial in log of 1 over epsilon. So in other words, the question that we're asking here is, can this gradient descent problem be solved in time that's polynomial in log of 1 over epsilon? Now you might wonder, is that too much to ask for? Can we even hope for something like this? And one example where it is possible is if the function f is convex. If the function that you're trying to optimize over is convex, then using, for example, the ellipsoid method, the dependence on epsilon is going to be of the form log 1 over epsilon. So there you can solve the problem with high precision. So you can think of this question as being, can you find a gradient descent solution, stationary points, in other words, with high precision? Can you do that efficiently? So this problem, because the input is given explicitly to you, you can study this in the standard Turing machine model, which has these classes, NP, etc. So it turns out that for this problem, the classes that we'll have to use are a bit different. And let me provide some examples to explain why. So let's take a look at some interesting computational problems that have something in common with our gradient descent problem. So the first problem is going to be Nash. Given a game, compute a mixed Nash equilibrium of the game. Then another very famous problem, factoring. Given a number, compute a prime factor of that number. The Brouwer problem, given a continuous function that maps the unit cube to itself, compute a fixed point of that function, namely a point x, such that f of x equals x. Special case of Brouwer, which is called contraction, which is given a function that's contracting, compute the unique fixed point of that contraction. From game theory, another problem, compute a pure Nash equilibrium of a congestion game. A congestion game is a type of game that's used to model traffic on road networks. And so here the problem asks you to compute a pure Nash equilibrium of such a game. And the last problem on that list is our gradient descent problem. So what do these problems all have in common? They seem pretty different. They come from different areas, but what do they have in common? It turns out that they are all NP total search problems, also known as TFMP problems. And that's because they have two crucial properties. The first one is that they are total. So for any instance of the problem, there necessarily always exists a solution. It's mathematically guaranteed. And the second one is that they lie in NP, in the sense that if I give you a candidate solution, you can verify efficiently if this is indeed a solution or not. So any problem that has these two properties lies in this class TFMP. Now, why is it important to note that our gradient descent problem lies in TFMP? Because of the following observation. Can a TFMP problem be NP hard? Should we attempt to prove NP hardness for any of these problems? And it turns out that no TFMP problem can be NP hard unless a collapse happens, namely unless co-NP equals NP, which is not believed to hold, at least by most complexity theorists. So unless you want to try to show that co-NP equals NP, you should not be attempting to prove NP hardness for these problems. So let me go over the definition really of this class really quickly again. So the class TFMP, which was defined by Megiddo and Papadimitriou in 1991, is the class of all total NP search problems. So there are three important things. The first one is that these are search problems, not decision problems. We're not just looking for a yes/no answer. We're actually looking for a solution. The problems lie in NP, in the sense that if you give me a candidate solution, I can check in polynomial time if it is indeed a solution or not. And finally, and crucially, the problems are total. Namely, it's mathematically guaranteed that for any instance, there necessarily exists a solution. So if you go back at a list of problems, the existence of a solution for the Nash problem is guaranteed by Nash's theorem, which tells you that every game has a mixed Nash equilibrium. For factoring, we all know that if you have a number that's at least 2, it has to have a prime factor. For Brouwer, the existence of such a fixed point follows from a topological result, which is called Brouwer's fixed point theorem. For contraction, the existence and uniqueness of a fixed point follows from Banach's fixed point theorem. For the congestion problem, it's a well-known result in the literature on congestion games, that there always exists a pure Nash equilibrium. And finally, for the gradient descent problem, why is there always a solution? well, since we're over a compact domain, the function has to have a global minimum, and that global minimum is in particular going to be a stationary point. Of course, there might be other stationary points as well that are not global optima. Okay, so this class TFMP is a set of all problems with these three properties. And it's quite interesting because in a certain sense, it lies between P and NP, or rather the search versions of these classes. And the reason is that it's not believed to be equal to P, because there are many problems that seem very hard in that class. On the other hand, it's not believed to be equal to the search version of NP. And the reason for that is what I mentioned on the previous slide, namely that no TFMP problem can be NP hard unless NP equals conp. And proving this is actually not too hard. Let me just briefly sketch that. Assume that you had a polynomial time reduction, let's say from 3-sat to the Nash problem. Now, using such a polynomial time reduction, because the Nash problem always has a solution, and you can efficiently verify solutions of the Nash problem, you would actually get polynomial time certificates for all 3-sat instances, including unsatisfiable 3-sat instances. So you would get short certificates that prove that some 3-sat instance does not have a solution, does not have a satisfying assignment. And that's exactly what would bring this collapse of co-NP to be equal to NP. Okay, so NP hardness is not an option. What's the next best thing we could hope for? Well, we could hope to show that some problem in TFMP is as hard as any other problem in TFMP, which is essentially what you do in NP when you prove that a problem is NP complete. But here, because of how general this TFMP class is, in the sense that it has this property of totality, any problem that is guaranteed to have a solution is included in this class. And that's a very general property that can come from very different types of proofs. So because of the way this class is defined, it's not believed that it has any complete problems at all. So that's not an option either. But as I said, there are many problems that are believed to be hard. So what can we do in order to provide evidence that the problems in this class are actually hard? So what Papadimitriou proposed around 30 years ago is to investigate the landscape inside this class TFMP, to define subclasses of TFMP that are nicer, that have complete problems, and to try to classify all of the natural problems that we care about in terms of these subclasses, in order to ultimately understand how the problems relate to each other, which problems are easier, which problems are harder, etc. So various subclasses have been defined. I'll just mention a few of them. So there's a class that's called PPP, which is associated to the pigeonhole principle, in the sense that it contains all the TFMP problems, but the existence of a solution is guaranteed by the pigeonhole principle. So the proof of existence of a solution, the main ingredient of the proof, is an application of the pigeonhole principle. Another class is PPA, and here the existence is guaranteed by some kind of a parity argument, like the handshaking lemma, for example. This class also has a nice characterization in terms of topology. So you can also think of this class as containing all the problems with the existence of a solution is guaranteed by the Borsuk-Ulam theorem, which is a theorem from topology that has been quite useful in combinatorics in particular. So these are two classes, but there are two other classes that have been actually much more successful. The first one is PLS. PLS contains problems where the existence of a solution is guaranteed by some kind of local search argument. And PLS has been very successful in exactly capturing the complexity of various local search problems. For example, it turns out that this pure congestion problem that I had earlier on the slides, computing a pure Nash equilibrium for congestion game, this is PLS complete. Another PLS complete problem is the local max cut problem, where I give you a weighted graph with weights on the edges, and I ask you to find a cut which is maximal up to local changes, where local changes means you can just switch a vertex from one side of the cut to the other one. So finding such a cut that's optimal up to these local changes is PLS complete. And PLS more generally has been very successful in capturing the complexity of problems where you're looking for a locally optimal solution. The other class that's been very successful is PPAD. So PPAD contains problems where the existence of a solution is guaranteed by some kind of a directed graph argument. I won't say more about this here because we'll see the definition later. Importantly, the class is mostly known because it exactly captures the complexity of computing a Nash equilibrium. And it also has a nice characterization. You can also think of PPAD as containing all the problems with the existence of a solution is guaranteed by Brouwer's fixed-point theorem. More generally, this class PPAD has been very successful in exactly capturing the complexity of problems from game theory, economics, etc. So we have these two very successful classes, PPAD, PLS. There's one problem that's missing from this picture, which is the factoring problem, a very important problem. So where does it lie in this picture? The answer is we don't really know. We have some partial results. So it's known that factoring lies in PPA and in PPP under randomized reductions. That's why I put it halfway in there. But we don't know exactly where it lies in this picture. It could very well lie down here in P. It could lie in PPAD or perhaps not. We don't know. And that's an important open question. So the famous result that Nash is PPAD complete is interpreted as saying that the problem of computing a Nash equilibrium is computationally intractable, not solvable in polynomial time. Well, why does one interpret such a PPAD completeness result in that way? What evidence is there that PPAD is actually a hard class or PLS is a hard class? So what reasons are there to believe that these classes are not actually just equal to P? I can give you three reasons. The first one is that there are a lot of seemingly hard problems that lie in these classes, a lot of problems that are natural, so they come from various fields where people have worked on them for quite some time, and they've not been able to find a polynomial time algorithm. So that's one first type of evidence. Another reason is that there are oracle separations between the classes and between the classes and P. Again, oracle separations are not always right, but it's some kind of evidence. Finally, perhaps more convincing, is that they're known to be hard under various cryptographic assumptions. In other words, we know that, if PPAD were equal to P, then that would imply that some cryptographic primitive that we believe exists is not going to be possible. At the moment, the cryptographic assumptions that are used are not completely standard, but I believe there's been some work lately that has made a great improvement over that, and the assumptions are now almost standard. Let's get back to our picture, and let's get back to our problem of interest, which is this gradient descent problem. So where does it lie in this picture? And it turns out that the problem lies in both of the successful classes, PPAD and PLS. So it lies over here in the intersection. And let me briefly explain why it lies in both of these classes. So let me zoom in just into these two classes, PPAD and PLS, with some complete problems for each of the two classes. So recall that in the definition of the gradient descent problem, there were these two different versions of the problem that we could consider, which were polynomial time equivalent, but there were two different ways of defining the solution concept. And one way was to say, we're looking for a fixed point, essentially, of the gradient descent dynamics, namely a point where the next iterate is very close to the current one. And that problem, we called it GD fixed point. And now this problem, because you're essentially looking for a fixed point of the gradient descent dynamics, it turns out that it's a special case of Brouwer. And as a result, the problem lies in PPAD. Now, if you consider the other version of the problem, where we're thinking of it more as a local search problem, maybe we're saying, a solution is a point where the next iterate does not improve the function value by much. And that version was the GD local search version of the problem. It turns out that this problem lies in PLS because it's a local search problem, essentially. Now, because these two problems are actually polynomial time equivalent, what that means is that the gradient descent problem lies in both of these classes. So it lies in the intersection, PPAD intersection PLS. Now this class has been studied in the past. Around 10 years ago, Skalakis and Papadimitriou, they noticed that there's quite a lot of natural problems that actually lie in both of these classes, both in PPAD and in PLS. Let me just give a few of them. So the contraction problem that we saw earlier, find the unique fixed point of a contracting function, the problem of finding a mixed Nash equilibrium of a congestion game, as opposed to a pure Nash equilibrium, the problem of solving P matrix LCP, which is a linear complementarity problem, a generalization of linear programming. That problem also lies in this class. The problem of computing a fixed point of a function where the existence is guaranteed by Tarski's fixed point theorem, the problem of solving a simple stochastic game, etc. So there are many natural problems that lie in this intersection. And because it's not believed that PPAD is a subset of PLS, or that PLS is a subset of PPAD, the problems in the intersection cannot be complete for any of these two classes. So what is the correct classification for these problems? Could they actually be complete for the intersection? Could any of these problems be PPAD intersection PLS complete? So the Skalakis and Papadimitriou considered this question, and they made the following argument, saying that actually this class PPAD intersection PLS seems quite unnatural. So let's do the following. Let's take any PPAD complete problem A, for example, Nash, and any PLS complete problem B, for example, local max cut. And let's define the following problem that combines the two. So the problem is called either solution of A or B. The input to the problem is any instance of problem A and an instance of problem B. So I give you an instance of problem A and an instance of problem B. And the goal is to find a solution of one of the two instances. So I give you an instance of problem A, an instance of problem B, and I just ask you to solve one of the two, whichever one you prefer. I don't care which one, but solve one of the two. So it's not too hard to show that this problem is essentially automatically PPAD intersection PLS complete. If the problem A is PPAD complete and the problem B is PLS complete. And this works more generally for any two TFMP subclasses. If you combine two problems like this, you get a problem that's complete for the intersection. So that's very nice. We have a ton of complete problems for this class here, PPAD intersection PLS. The problem is that these problems are quite unnatural. You've just taken two unrelated problems and you have combined them in an artificial way to get a new problem. This doesn't look like any natural problem. And so the Skalakis and Papadimitriou said, well, this class PPAD intersection PLS is unlikely to be the correct class to exactly capture the complexity of natural problems. And they defined a different class, which they called CLS, for continuous local search, which combines PPAD and PLS in a more natural way. And it's a subclass of PPAD intersection PLS. It's defined using a complete problem that's called continuous local opt. And you can think of it as just a special case of PLS with more continuity. So they proposed this class as a better alternative to PPAD intersection PLS, namely as being more likely to be the class that's going to exactly capture the complexity of these natural problems that we care about. And in order to provide evidence for their point, they prove that a lot of these natural problems that lie in PPAD intersection PLS, they actually lie in CLS as well. So all these problems that I mentioned earlier, turns out that they also lie in CLS. And so the argument was that CLS is more likely to be the correct class to capture the complexity. Now, coming back to our gradient descent problem, it's actually not hard to show that gradient descent is a special case of continuous local search, and as a result, it lies in CLS. So yeah, this problem here, Banach, is essentially the only other CLS complete problem we know in the past 10 years. So there hasn't been much progress in actually proving that any of these problems is CLS complete. So the gradient descent problem lies in CLS because in a certain sense, it is a continuous local search problem. So the question is it actually complete for CLS? And so our main result is to show that it is complete for CLS, but not only for CLS. It is actually complete for PPAD intersection PLS. So this problem gradient descent, which lies inside CLS, is actually as hard as a bigger class around it. What that means is that actually these two classes they're not different, they're actually the same thing. In other words, the two classes collapse to a single class. And so the updated picture looks like this. PPAD intersection PLS is the same as CLS. It has all of these complete problems, including the gradient descent problem, and it contains these various problems, these various natural problems for which we don't have a hardness result yet. So what are some consequences of this collapse here, this class collapse, which was quite unexpected? The first consequence is that it turns out that this class PPAD intersection PLS is interesting after all. Even though it looked very unnatural, it has this weird artificial complete problems. Turns out that it has much nicer natural complete problems. In fact, it has a very nice characterization in terms of continuous local search, or even just gradient descent. You can think of this class as just being the class of all problems that can be solved by gradient descent, that can be reduced to the gradient descent problem. And there are also some technical consequences. The two-dimensional problem is just as hard as a high-dimensional. The domain can be very simple, doesn't make the problem any easier, etc. So this follows from the exact reduction that we get. So in the remaining time of this talk, I'm going to present a very high-level proof sketch of the result, namely of the main theorem. So what is the main theorem? The main theorem is that the gradient descent problem is PPAD intersection PLS hard. This is what provokes this collapse, the fact that the gradient descent problem is just as hard as the bigger class. So how do you show a result like this? Well, you have to provide a polynomial time reduction from some PPAD intersection PLS complete problem to the gradient descent problem. So the only complete problems we know for this class are these weird either solution problems that combine the two problems in an artificial way. So we're going to reduce from such an either solution problem with PPAD and PLS to the gradient descent problem. And in fact, just a two-dimensional gradient descent problem is already going to be enough. It's already going to be just as hard as a high-dimensional problem. At a very high level, what does the reduction do? First of all, defines the value of f and its gradient on a very fine grid over the domain, the square domain, which is going to be our domain. Then, once that's done, it's going to use a special kind of interpolation, which is called bicubic interpolation, to interpolate between these points and to obtain a smooth function over the whole domain. And then you just have to show that any gradient descent solution, so any stationary point, is actually going to give you a solution either to the PPAD problem or to the PLS problem that you had. If you do this, then you've shown the reduction. So in order for me to give you a bit more details about the reduction, I need to define PPAD. So PPAD is defined using a canonical complete problem, which is called end of line. So what does this problem look like? So the input is a directed graph of paths and cycles. So that means that every vertex has out degree at most 1 and in degree at most 1. So the graph looks like this. It only has paths and cycles. So I give you this graph, and I also give you one specific source. For example, this source over here, the blue square source. And what is the goal? What do you have to do to solve the problem? You have to find a sink of the graph or any other source other than the blue square source. In other words, the solutions are these red stars. Any of the red stars is an acceptable solution. Note that the solution will always exist because the line that starts at the blue square has to finish somewhere. So that's at least one solution that's guaranteed to exist. But of course, there might be more solutions. If you look at this problem, you might say, wait, there's something wrong here. This problem is easy to solve. I'm just given the graph. I can just explore it and find a solution. So there is a catch. And the catch is that the graph is not given explicitly to you. It's only given implicitly. In other words, the vertex set of the graph is all the bit strings of length n. So it has, potentially exponentially many vertices in n. And you just have two Boolean circuits, S and P, that compute the successor and predecessor. In other words, you input a node, it tells you what the next node on the line is, or the predecessor circuit tells you what the previous node on the line is. In other words, you can take a single step on the graph in polynomial time, but the whole graph might be exponential in its representation. So it might be too big to actually explore in polynomial time. And this is what makes the problem non-trivial to solve. The fact that the graph can be huge, actually, compared to its representation. So this is the end-of-line problem, and this is a problem that we use to reduce from for the PPAD problem, the either solution problem. I won't say what the problem is exactly for the PLS complete problem, but it won't matter here for the high-level idea. Okay, so now we can restate what we want to do. We want to reduce from the either solution problem, where the first problem is end of line and the second problem is some PLS complete problem. To be more specific, we want to construct a continuously differentiable function from the unit square to the reals, such that any gradient descent fixed point, any stationary point, is a solution to this either solution problem. So how do we do this? We're going to start with a base function, a very simple function, which is just defined like this. So the arrows here, they show the direction of steepest descent of the function. In other words, the direction in which gradient descent will go if you run it on the function. So the function that we define has a trivial gradient. The gradient just points down to the left. It points down here. And as a result, the only gradient descent solution of this function is the origin down here, because this is where gradient descent is going to end. It's the only KKT point of the function. So I've represented the function here in terms of the direction of steepest descent. What does the function actually look like? It's simply a function like this, which is just a plane that's inclined towards the origin 0, 0. Obviously, this function it's very easy to find a stationary point. You know that it's over here. So now we're going to perform some small local modifications on this function in order to do the reduction. But the starting point is this function. So it turns out that what you can do is that you can take this trivial solution at the origin, and you can hide it inside the instance by creating this green path over here, where again, the arrows, they show you the direction that gradient descent will take. And so you can think of this as gradient descent pushes you down here, but then here it goes in this direction and it goes to the end of the path. And then this is the only, gradient descent solution of the function. And how should you think of this function again? How should you picture it? Well, this green path, you should think of it as having function value that's much, much lower than the rest of the function, than the base function. So you can think of it as a deep valley that goes deeper and deeper as you progress, or as a very deep ravine, just goes deeper and deeper. That has a much lower function value than anything around it. Okay, and then intuitively kind of makes sense that the only gradient descent solution is going to be at the end of this ravine. So this first observation is already enough to get a partial reduction. So let's consider a special case of the end-of-line problem. I'm going to call the monotone end-of-line problem, where the vertices are numbered and you have a guarantee that the edges of the end-of-line instance, they only go forward with respect to the numbers. In other words, the successor of some node has to be a node with a larger number, a larger ID. You have no backwards edges from 6 to 4 or from 7 to 4. That's not allowed, only forward edges. Again, the rest of the definition of the problem is the same. You're given a source and you want to find any end of lines, so any other source or any sink. So the observation that we had earlier is actually enough to reduce from this problem. How? Well, let's just think of all the nodes as lying on the diagonal of our domain. And for each edge of the end-of-line instance, let's just implement it by using this deep valley ravine technique. So for the first edge going from 0 to 1, let's just have this valley going from 0 to 1, and the same for edges from 1. There's an edge from 1 to 3, so there's going to be a valley going from 1 to 3. And here at 1, obviously the valley that arrives is going to connect with the next valley, and the same thing here at 3. And you do this for all of the edges. And once you've done this for all of the edges, you've actually encoded all of the edges of the graph. And it turns out you can show that the gradient descent solutions are only going to occur at the end of a valley or at the beginning of a valley, except of course the beginning down here, because that one, as we saw earlier, there's no solution there. The solution is at the end of the valley. What does that mean? Well, it means that there's going to be a solution at 2, at 4, and at 7. And these are exactly the solutions of our monotone end-of-line instance. So if your end-of-line instance has this monotonicity property, then this idea is already enough to reduce to the gradient descent problem. But that's not enough for us, because we have to reduce from the more general problem. So this idea here is actually essentially follows from existing work by Hubacek and Yogev. Just need to show that all of these things are locally computable in a certain sense. Okay, so we want to reduce from the original, more general version of end-of-line, but we didn't have this monotonicity. Now, when you don't have monotonicity, you can still, assign numbers to the vertices. You can order them, but you no longer have the guarantee that all the edges are going forward. For example, here we have an edge going backwards, and here as well. So what we're going to do is that we're going to differentiate between these two types of edges that go forward, which we'll call green edges, and edges that go backwards, which we'll call red edges. So going back to our reduction, we know how to implement the green edges. That's what we did before. We just create these deep valleys, and we can implement the green edges. Of course, the issue is that that's not enough, because if you look at the solutions now, 4 is a solution, 5 is a solution, and 7 is a solution, even though in this original instance, 3 was the only solution, the only end-of-line. And that's because we have not implemented the backwards edges. So it turns out that you can also implement the backwards edges, the red edges, by creating such a red path. Again, the direction of the arrow shows you the direction that gradient descent would take. And you should think of this red path as kind of the opposite of a green path. Namely, instead of having a very low function value, you have a very high function value, much higher than the rest of the function around it. So you can think of this as a very high mountain ridge that goes higher and higher as you go in this direction. And the same here, high mountain ridge that goes higher and higher as you go like this. So that's good. We've implemented the red edges as well. But there is an issue. The issue is that the nodes 4, 5, and 7 are still solutions. Why is that? Well, if you think about the green paths here, there's a deep valley going deeper and deeper and deeper and arriving here. It's going to be a local minimum. All the values around it are higher than this end of valley. And similarly, this is a mountain ridge that goes higher and higher and higher. And when it arrives here, it's the highest point. There's no other point that has a value as high as that around it. So it's going to be a local maximum. So in particular, a stationary point. What that means is that actually it's unavoidable when you have this green and red path that meet either at node 4, 5, or 7, you're going to have a stationary point. In this specific example, it's the end of a green valley, so you have to have a local minimum. It's unavoidable. So it is unavoidable, but what can we do? So the idea here is to say, okay, there's going to be a local minimum here, but let's hide its exact position. So what we do is we create a gadget that we call the PLS labyrinth, which actually hides the exact position of this local minimum. And it hides it in such a way that locating its exact position requires solving the other problem, the PLS problem. And it turns out that you can do this whenever a red path meets a green path. So you can do it over here, and over here. And as a result, let's look at what the stationary points of this function are. So there are stationary points in all these regions, 3, 4, 5, and 7. If you give me the stationary point in this region, that's a solution to the end-of-line instance, so I'm happy. If you give me the stationary point in this region here, 4, then from the exact coordinates of that stationary point, I can find a solution to the PLS problem. Similarly, if you give me the stationary point in here or in here, by looking precisely at the coordinates, I can find out a solution to the PLS problem. And that's exactly what we want. We want to be able to solve the PPAD problem, namely end of line, or the PLS problem. One of the two. We don't care which one, whichever one. As long as I get a solution to one of the two, I'm happy. And this is essentially why the reduction works. Now, the details are a bit uglier because you have to define the function on a discrete grid, and then interpolate by using a special kind of interpolation. But the high-level idea presented is really what's going on. So let me finish by mentioning some future directions. The first one is, okay, so it turns out that taking the intersection of seemingly unrelated classes can give something very interesting. Other examples of classes where you just take their intersection and you get something that's interesting that captures natural problems, or is this really just a special case? Did we just get lucky? And another important future direction is to say, okay, now we know that this class PPAD intersection PLS is natural, that it's likely to exactly capture the complexity of natural problems. Let's try to prove that. Let's try to prove that some of these problems that lie in PPAD intersection PLS are actually complete for that class. And some examples are the contraction problem, the problem of computing a Tarski fixed point, of computing a mixed equilibrium of a congestion game. And it turns out that this last problem has actually been solved. So in follow-up work by Babichenko and Rubinstein, they were able to show that this gradient descent problem that we've been working with in this talk reduces to the problem of computing a mixed Nash equilibrium of a congestion game. And so this means that this problem is PPAD intersection PLS complete. Let me mention another related work, which is if you do the same kind of stuff, but not for minimum optimization, which was the original problem we had on the first slide, but instead you do min-max optimization, which is a harder problem, there it turns out that the corresponding stationary point problem is PPAD complete. So harder, which makes sense. Yeah, thank you. That's all I had. Happy to take questions.
Thank you, Alex, for a very nice talk. Let me see. I can see one question in the chat, which says, can we use gradient descent without hidden layer? I'm not sure I understand the question, but do you?
Maybe the person who asked the question can.
Yes.
Can ask it in person.
Yeah. Let me see. I think I'll find the person. Siddhartha Chatterjee. Raise your hand. Yeah. Good. I'm gonna unmute you. Yep.
Yes. Am I audible to everyone?
Yes.
Hi.
Hello. Yes. Yes. Am I audible?
Yes. Yes, you are. Yes.
Yes. My name is Siddharth Chatterjee, Dr. Siddharth Chatterjee. I am from India. Okay, right. So I have one question. The question is, normally in backpropagation technique, we use partial derivative oriented gradient descent problem, right? So my question is, can we use this gradient descent technique or this method without any hidden layer? Because in case of any hidden layer, we use this technique for find out the back error, basically back propagation error. But here my question is, can we use this technique without hidden layer?
I'm not sure if I understand the question. I mean, this is just we're just looking at how hard is it to find.
Backpropagation is backpropagation technique is one of the technique in a neural network, basically.
Yeah.
This technique we can find out the backpropagation error, right? It's one type of neural network model. So in this technique, we use gradient descent technique, right? and also in backpropagation technique we use some hidden layer. Okay, input layer, then some hidden layer, then output layer. But here my question is, can we use this gradient descent technique or process without any hidden layer?
So this result here, it applies to the case where the function is given explicitly to you. But obviously it's a worst case result. So it applies to some, specific functions that were constructed to be very hard. And the functions that you get from in practice in machine learning, they're probably not these worst case hard functions. So the hardness result that we prove here, it probably doesn't apply to the specific functions that you get in practice or that people usually see in machine learning. It's a worst case result. And I think it's an interesting question to try to extend it to specific functions that occur from machine learning applications.
Yes.
From neural networks, for example, the function f that you get when you try to run gradient descent on a neural network, can you prove that that's also hard, or is it easier for some reason because it has some extra structure? That's an interesting open question.